We've been using exhaustive algorithms, guess and check algorithms, to solve some simple numerical problems. But if you think about it, they've all been doing things with integers, where there is a finite number of choices that we have to check. And that makes sense. I can certainly run through all of them until I get to either the right answer or determine there isn't a possible answer. But now suppose we want to find, say, the square root or the cube root of any non-negative number. It could be an integer, it could be a float, it could be any number. I can't generate all possible guesses. They're infinite. So I can't, in this case, guarantee an exact answer, but I could come close. Now what I just want to do is try and find a guess that's close enough to the cube root or the square root of the thing I'm looking for. I can still use that notion of exhaustive enumeration, but I'm going to now have to pick examples where I take small steps in order to generate the guess and check to see if I'm close enough. Let's see what that might look like. Here the idea is I have to define what's a good enough solution. So I'm going to start with a guess, say 1. I'm going to check to see if that's close enough. If it isn't, I'm going to change it by a tiny amount, say 1.001. Check that one, and then 1.002 and keep doing that. So I need to increment by some small value as I go along. But I also have to define what does it mean to get close enough. It won't be exactly the same because I'm not going to be able to guarantee that. So here I'm going to use, in the case of cube root, something that tells me whether I'm close enough. By looking at the guess cubed, take the absolute value in case it's negative, and look at the difference between that and cubed to see if it's less than or equal to a small number. And if it is, I'm going to say I'm close enough, and I'm going to stop. One of the tricks here is that when I have these small values, I'm going to have to be careful. If I make them really small, I'll make sure I find a really good guess, but it's going to slow the program down. If I make them really large, I might actually miss the answer. And similarly, when I decide how close I want to get with epsilon, if I make epsilon big, I'm going to make it easier to find an answer, but I might get a less accurate answer. And so I have to think carefully about how I do both of those. But let's look at that idea to see how I can still use the idea of guess and check, but now with things that could compute the cube root of anything. So here's an example. I'm going to start off with some value for the thing I'm trying to find the cube of. 27 is going to be an easy one. I'm going to set up some initial values. Epsilon is going to be something that tells me how close I want to get to the answer. Guess is where I'm going to start. And increments the size in which I'm going to increase my guess as I move along. And just to keep track of it, I'm going to set up another variable called number of guesses. I'm going to use that to keep track of how many times do I go through the loop as I do this. And then what does this code do? It says while the difference between the cube or the guess cubed and the thing I'm trying to find the cube root of, while that difference is still bigger than epsilon, I'm going to keep going by incrementing guess by increment. There's that plus equal that I've used before. And changing number of guesses by 1, saying I've done another guess and keep going. I'm going to keep doing that until I get to something where the difference between guess cubed and cube is small enough, and at that point I'm going to stop and I'm going to return both how many guesses did I run and some information about did I find the right answer. Let's see what happens if I run that. So there's a piece of code. Let me start with 27, which is the thing I had before. And if I load that and run it, it gives me not quite the answer I expected. It says 2.9970000001906 is close to the cube root of 27. And that's true. We're going to see in a little bit why it doesn't just give me 3. It gives me this funny answer in there. But you can also see that it took almost 30,000 times through the loop before it got to that. Why? Because I started with a very simple answer, 0. That wasn't close enough. Then I went to 0.0001, then to 0.0002. And you can see I'm going to have to do a lot of things until I get to something that's going to give me a good guess. Now, I could pick another example. Let's make it 29, which I know is not a cube root. Let's see what happens if I do that. It's not a perfect cube, but in this case, it found it. That's actually nice. In the previous case, I could only find things that were cube roots of integers. Now I've got something where the cube root isn't an integer, but I can still find it. This took almost 31,000 times through the loop. So I could say, you know what? I want to use something where I'm going to step a little more broadly. Let's step thousandth of a step rather than every 10,000th of a step. And now if I run it, okay, I get a little bit different guess, but it only took 3,000 trials through it. And if I change it to say the increment should be in hundreds, I can run that. And if I do that, oops, sorry, it decided it didn't like that. Let me think about why it didn't like that. What's happened here? It's off in an infinite loop. And the reason it's off in an infinite loop is because I'm checking only to see if I get to a place where it's close enough. I've actually gone right past the cube root and it's still running. So I need to stop this and I'm going to interrupt it to hold it back. That's something I need to fix. So if I go back to a little bit better increment here and rerun it, I get back to the thing I wanted to have. Okay, how would I fix that? I need to make sure that the guess isn't too big. If you think, and I'm going to go back to where I was. With this test, it simply says when guess cube minus cube, as long as it's bigger than epsilon, I'm going to keep going through the loop. If my step is too big, I could try something just below cubed, but not have it work, and then go past cube and keep going further and further on. That says I need to make a change here, so I want to make sure that my guess is still small enough. And if I make that small change, which I'm going to do over here, and guess less than or equal to cube, I should be in a little bit better shape. I can still run the same one, but now if I change increment to tenths and run that, it gave me a solution. Not a very good one. It basically says I didn't find a solution, but at least I didn't keep running forever. What was the point of doing this? It's not to try and trick you. It's to remind you that as you make changes to the code, you need to think about the consequences. And this was one where my test wasn't capturing all of the cases. So what can I say about this particular algorithm? The step could be any small number. If it's too small, it's going to take a long time. But as we just saw, if it's too large and I'm not careful, it could skip over the answer without getting close enough. At least in this case, I stop rather than running forever. In general, it's going to take x divided by step number of times through the code to find a solution. And so clearly, as I make steps smaller and smaller, it's going to increase the number of steps, and I'd like to find a more efficient way to solving this problem.